too.
Very well. Okay. So Erden, switch on the video. At least I see your face.
Okay.
You have a beautiful face of a Turkish soldier. You know, in Italy we say "Mamma li turchi."
Yeah,
They are afraid of the arrival of Turkish people. Okay, so let's do a new kind of reasoning. So this one could forget any variational principle simply by exploiting an important consequence of minimality. So I want to show you what happened. Okay, so maybe we can hope that we will be soon able to write, for instance, with Erden and with Alessandro, a small historical paper where we fully report this shift. We could call it a shift of paradigm. It's very strange that in English, a word which is Greek and should be read paradigm is read paradigm. So what happened? You decide to base every reasoning on balance of forces and moment of forces. I'm sure that everybody among you has seen some plot like that. You have the externally applied forces, you have the reactive force, the constrained forces, you have volume forces. So maybe let us keep using the same, always the same notation. So we have and in order to verify equilibrium, okay, one calculates the resultant force and resultant moment of forces and uses these equations for finding unknowns. So this is more or less a reasoning due to Cauchy. And I can prove you making some detailed analysis of sources that Cauchy made this reasoning. After Piola's reasonings. So what I claim is that Cauchy knew the result, and knowing the result, obtained it in a different way. So I want to show you quickly how this can be done. Probably you already did it in some courses. And I want to show you how this is useful for simplifying the presentation of fluid dynamics. So let us recall what we did. We have a reference configuration. We have placement. We have the actual configuration. Okay. Then we wrote integral of W of F in the reference configuration. This is the deformation energy. Then what we did? We calculate the first variation of the deformation energy, which is a linear function of the small variation of placement. Okay. Then after this, we found the set of external forces applicable to a first gradient continuum. Okay. And after this, we wrote the total energy, the admissible total energy. So we wrote that the total energy is equal to the deformation energy plus integral on C star of minus B volume external dot key. This is potential energy of the volume forces plus the integral on the boundary of C of minus Bx sigma dot key. And this is the external potential, the potential of external forces on our body. Then we change the variable here. So we wrote this like integral over C of minus B tilde x V dot key. Why? Because, you know, you change dV into dV star with the Jacobian determinant, and you similarly change the area in the actual configuration with the surface Jacobian determinant of the change of variable. So we wrote the external forces in the actual configuration. Okay. And then calculating the first variation of E dot for rigid virtual displacement. So here we place delta key equal delta U0 plus delta theta vector small x minus small x0. We observe that the deformation energy must be 0 for every variation, which is a rigid body displacement. And what we have proven that the resultant force Eulerian in Eulerian description is equal to 0, and the resultant moment of the forces with respect to every reduction pole is equal to 0. And these are the cardinal equations for dynamics. So what we have proven is that a necessary condition for equilibrium is that the total, the resultant force of the, of course, you must consider every force applied to the body. And this is the reason for which, if you have a part of the boundary which is blocked, you need to introduce constrained forces. The resultant of all forces, active and reactive, and the resultant moment of all forces, active and reactive, must be 0 if we know that the system is in equilibrium. Okay? So one could decide to limit the analysis to the cases where this necessary condition is also sufficient. And Cauchy, without telling it too much explicitly, made this choice. However, in order to proceed, Cauchy had to invent the concept of sub-body. So let us reason a little bit about this. So we forget for a while the reference configuration, and we stay only Eulerian for the moment. We consider one equilibrium actual configuration of our body. So this is only C, okay? And we must introduce every external force applied. Okay, so we know that you have B sigma on the free boundary. You have B sigma constrained, and you have B volume. Okay. Now, if we write only resultant forces equal 0, so if we write integral over the whole C without the star of B volume plus integral on the boundary of C of B sigma C okay, we keep splitting the boundary, the free part of the boundary and in the constrained part of the boundary. And the other equation for the moment okay, I write B tot, and in this way I save one integral. The formula is shorter. Clearly, these equations are not enough for determining the equilibrium configuration. You remember, I repeat the famous joke of Professor Di Carlo. The story I told you one time, and probably it is worth to repeat it to you. The poor student, having decided that a system of forces equivalent to 0 could be studied as if no forces were applied to a body, was ideally placed, you know, in United States, but maybe even now in Italy, the student would have called police for this joke. But, you know, I'm talking about something which happened 25 years ago. So the idea is that he had to understand rather quickly, being afraid to be killed by 4 horses, that for the formable bodies, the cardinal equations of dynamics are not enough for characterizing the equilibrium configuration. You need to give information about what is lacking. What is lacking? Informations about EDF, which is not appearing here at all. So about the possibility of the body to be deformed or not. And then, as a consequence, informations about the parts, the deforming parts of the body. You know, imagine that you have this body and you have some forces here and there. Okay, in order to find equilibrium, you must know possibly that this part is made of aluminum and this part is made of iron. So in order to be sure that equilibrium is attained, you must know that every sub part of your body is in equilibrium. So let us think about what is happening. You are like Cauchy, afraid of variational principles. Okay, you know, I am rather critical about Cauchy in general because in his life, you know, I've read this story, what he wrote. You know, he was a man whose behavior was not so clear in all his life. But this is, in this context, not so relevant. Why? Because Cauchy, you know, you could suspect that he was reading the results of Piola and he wanted to claim that he had obtained them, so he decided to use another method. But you know, it could be a positive interpretation. One could find a positive interpretation about Cauchy choices. Cauchy probably was afraid of those aspects of functional analysis that he did not control fully. And nobody did control these aspects those times. I told you that Sobolev understood the most important parts of the theory used by Lagrange and Piola some 100 years later. So probably he was simply looking for an equivalent way or another path towards the results which I have shown you. Okay, so what he did, he considered the equilibrium configuration. Then he introduced Cauchy. So he invented a mental splitting of the body C into two sub-bodies. Two sub-bodies. So if the surface sigma has the normal n, let's call it small n, for keeping the notation. Everything Eulerian is small and everything Lagrangian is big. So maybe we call small sigma here. Okay. So what imagined? I said, let us imagine to remove the part of the body which is in the direction of the normal which I've chosen on sigma. So we remove this part and we consider only, so this is the plus part and this is the minus part. We remove C plus and we focus on C minus only. Okay. And by considering C minus only, C plus is external. So the interaction between C plus and C minus, so that the interaction between C plus and C minus are to be included in the balance of force and moment of force. Okay. So up to now, this reasoning is rather appealing. However, I want to remark that if before the Cauchy cut you had a boundary which is regular, after the cut you have new corners which are appearing. And we will talk about this later, and this could give difficulties. But you know, what Cauchy made, calling small n the normal of the Cauchy cut he has introduced, Cauchy assumed that the interaction between C plus and C minus can be described by forces per unit area. So he introduced what is called the Cauchy vector field. In every point, he has a force per unit area, and the contact interaction between C plus and C minus is given by the field T, constituted by the so-called Cauchy vectors. So T of small x, where x belongs to sigma, is the force per unit area representing the interaction between C plus and C minus. Of course, you know, you must tell that T is the force of C plus on C minus, and then to make your life more complicated, if T is the force which C plus exerts to C minus, then minus T is the force that C minus exerts on C plus. So you must introduce action reaction principle. Okay, I'm telling you the story as presented by Cauchy with some, I try to do quicker, but okay. So you can see that you have a multiplication of principles. Okay. So what you have is that instead of having one principle, the principle of minimum of energy, while building the theory, in every step you need to ask for help. And you invent extra properties to go towards the results. I think that Cauchy knew the result as formulated by Lagrange and Piola, so that he could guess the right conjectures, the right postulates. This is, in my opinion, a fundamental statement which needs to be proved reading carefully the sources. Okay. Why it is so important, such a statement? This statement is important because we want to invent new things. And as there is no general theory on how inventing new models, we must see how in history of science new models were invented. So it is very important to understand if Cauchy could find the right result alone, or he was obliged, you know, like some students who go and read in the other people's book before finding the answer, if he had to get informations about what using another postulation was deduced. So Cauchy is in a very bad shape, I think, because what he has done up to now, he has cut the body into subparts, and he has associated a vector which represents a force per unit area, and this vector is mathematically modeling the interaction between C plus and C minus. So T, you agree with me, is an imaginary mathematical quantity without any connection with something we can measure. Okay, nobody is cutting a beam and applying forces per unit area to measure the internal strain deformation and the internal strain state or stress state of that beam. So it is rather surprising that engineers could persuade themselves that this vector is physically understandable. I mean, I have heard many persons claiming that there is a physical content in the vector t, while there is no easy physical content in the concept of deformation energy. I agree with you. The deformation F can be measured. This is the only thing which you can measure. Okay. If you had any experience in any measuring situation in the theory of deformable body, you know that with strain gauges, you measure elongations. So this is the only object which can be measured. Deformation energy and the Cauchy vector are both mathematical, W and F, T are both mathematical entities, which we must use as an artifact for building our theories. You know, there is a very nice scheme from philosophy of science. So here you have the mathematical world, and here you have the physical world. Here you have phenomena. Okay. Here you have mathematical objects. Some mathematical objects have a correspondence in the physical world. They are immediately related to measurable things. Okay. Other mathematical objects are useful only in building the mathematical theory. So, for instance, you postulate a W of F, a deformation energy. Then you take your body in the reference configuration. You impose that this part of the body is blocked. You measure the displacement of this part of the body. You make calculations and you find the minimum of energy. All this lives here. So you use deformation energy, you measure the shape of the body, you measure the imposed displacement. Then you elaborate these informations with your mathematical theory. So here you have W, here you have div P plus B equals 0. I mean, you have what you have in the mathematical world. At the end, you get the forecast equilibrium shape. Then you go down. Here is the measured equilibrium shape. Okay? Please think about these things when you are handling COMSOL. Okay? COMSOL is a part of the world here in the mathematical world. Okay? Nothing is real in COMSOL is producing a set of numbers you must interpret. Okay. However, after a complicated elaboration, some elements of the mathematical world are in immediate correspondence with the physical world, and you use abstract concepts. At the end of your process, you forecast something, so you get a calculated mathematical equilibrium shape, and then as shapes can be compared, mathematical shapes can be compared with real world shapes, you get a possible comparison of one specific mathematical object with the measured quantities. If the prediction is good, then you accept the model in the specific context with all the limitations we have spoken about. Okay. So WF, the deformation, and T, the Cauchy vector, are both mathematical entities. They are both complicated. However, W is scalar, is a scalar quantity, while T is a vector. So, simplicity should suggest to prefer the first one. But there is not only this request, this is not only simplicity, which indicate that the choice of basing everything on deformation energy is better than the choice of basing everything on this mysterious vector T. Because for continuing, Cauchy must introduce so-called Cauchy postulate. So if this is the normal of the Cauchy cut small sigma, and if T is the vector per unit area, so let us make the list. Contact forces are only forces per unit area. Second, T depends only on N. I place an arrow just to remember you. So what it means, I mean, this is, of course, many people say that this is obvious physically, but let us place many question marks around this. Okay. So you have an obscure force per unit area. So for instance, one could tell you why we don't have concentrated edge forces there. It could be that you have a concentrated edge force. So you have the edge and the surface. Why you have a force per unit area and you don't have forces per unit edge? You make the assumption there are no edge forces. Then you have a body in the actual configuration, and you have this Cauchy cut and this Cauchy cut. In this point, they are tangent, and the normal is the same. Okay, so you have sigma 1 and sigma 2. In general, in this point, you have T sigma 1 and T sigma 2. The value of Cauchy vector in the point small x where these two surfaces are tangent. Cauchy lemma claims that T sigma 1 is equal to T sigma 2 in X. So I want that you understand carefully. So let us zoom this. We make it bigger. You have these two surfaces, sigma 1 and sigma 2. Okay, so what is this? Is C plus sigma 1. Okay, and this is C plus sigma 2. And what you are telling that both C plus sigma 1 and C plus sigma 2 are exerting here the same force per unit area. So their difference, which is this one, is not influencing in any way the T vector in that place. How do you call this kind? How do you call this kind of hypothesis? A postulate. So the basic assumption, let's say one of the basic assumptions, of a theory Okay, in the books, this assumption is called Cauchy Postulate. Okay. And the use of the word postulate in this context is absolutely bad. because actually this is a constitutive equation. This tells you, it tells you how a specific set of deformable bodies interacts inside. So, to be more precise, how the sub-bodies of the body interact each other, or one with the other, okay? So it is very suspicious that he assumed that the vector t depends only on the normal. So in general, you have that t depends on the surface, on the Cauchy cut, and you assume that it actually depends only on the normal. Okay. Then I'm sure that you have seen we have no force, wish, and time to reproduce this argument fully, but maybe if somebody requires it, we can try to do it. You have the Cauchy tetrahedron argument. You choose a tetrahedron, and this face here has normal n, so I try to draw this. Okay, and you apply balance of forces and moment of forces to this sub body. Okay. So maybe I can ask to Erden in one of the next lecture to explain in detail the tetrahedron argument. I can give you some notes. But you know, the basic idea is I postulate that if this side is epsilon, I postulate for every T epsilon tetrahedron, the balance of force and moment of forces. In this tetrahedron, you have the surface force on the face whose normal is n, and then you know this triangle here, for instance, as normal minus E2. So writing the balance of force and moment of forces to this sub-body and calculating the limit when epsilon tends to 0 of the resultant force applied to T epsilon, you discover that Tn is equal to sum over I of T EI Ni, where n is equal to n, sorry, where Ni's are the components of EI. So you discover that balance of force plus T n equal T sigma plus T is a force per unit area plus no other forces, contact forces, are applied. All these assumptions, you see how many people usually forget about this and they tell you only the. All this implies that Tn depends linearly on n. Okay. So you have a tensor, a linear map, which maps the normal n into the force per unit area. And this is called the Cauchy stress tensor. Okay. Then T transposed is equal to T, you get from of moment of forces. Okay. Finally, and this is what we will now do in more details, you take a sub-body of your body in the equilibrium, and you can write the balance of forces for every sub-body. So you can write that. So you have S included in C, and you write integral over S of B volume in D volume plus integral on the boundary of S of T and the area equal to 0. And this is the balance of forces applied on S. And you claim that this is true for every S included in C. So you wanted to avoid every virtual displacement, and now you find yourself to have a formulation, integral formulation for equilibrium, which is valid for every sub-body. Okay. Having done a list of assumptions which sometimes you do not control fully, because you know the tendency to forget about this is very often observed. Okay, so if this sub-body has some, is not regular as it is now, maybe it is like that. Okay, and you have edges, changes of curvature here. This integral here is an integral per unit area. So this integral does not see these irregularities in the boundary of the sub-body. Whenever you can calculate the integral of the surface integral of the forces per unit area, it is okay. Okay. Very well. Then you make integral over S of B volume d volume plus integral on the boundary of S of Tn d area equals 0. You apply here divergence theorem. So you get integral over S of BV plus, I write small div of T because here you are deriving with respect to the small x, not with respect to the capital X. T volume equals 0. So that you have that this integral must be 0 for every sub-body. Okay. Now, technically, you have some difficulties. Because the theorem of the mean value is not valid for vector integrands. I will give you an example of this in another lecture. So you are in troubles. How do you get information about this equation? Look the big shame. You consider a generic U0. I don't know why they don't call it delta U0. You calculate the inner product with this integral. This du delta U0 can go inside because it is independent of the integration variable. And you get integral over S of delta U0 dot BV plus div T dV. What is this? This is the work of volume plus surface forces in the virtual displacement delta U0. But this is not said explicitly, okay? And this is equal to 0 for every S and for every delta U0. So what you can remark is that the results by Piola are artificially introduced in the new scheme. Okay. Now, this integral, you remember when we wrote this, we said equilibrium condition for rigid displacement. Okay. So as you have now a scalar quantity and the integral of this scalar quantity must be equal to 0 for every volume, you can do the standard trick. You take x, the ball of radius epsilon centered in x, and you calculate the integral over c x comma epsilon of delta u0 dot b volume plus div t, and this is 0 for every epsilon. So this is a scalar quantity. You can say that integral of cx epsilon of delta u0 dot bv plus div t is equal to the volume of cx epsilon times delta u0 plus bv plus div t calculated in a point xi inside the ball. Okay. And with some reasonings, you may deduce that this implies that bv plus div t is equal to 0. Actually, you must multiply here a function f of epsilon and x in order to have a delta Dirac inside, so that you simplify this. You simplify this volume here. I'm running on this, but we have already seen this point. However, please, Erden, check if this point is clear. Otherwise, we go back to this point. Okay. Today, I want to arrive at the end of the story, maybe running on some details, and we will cover the empty spaces later. Okay. So as a final result, you get div t plus bv equals 0 in Eulerian description. This is the counterpart in Eulerian description of div p. Okay, sorry, I was lazy. Here I should place tilde everywhere. So I go to place tilde everywhere. Because you have a Jacobian to be fixed. Okay. And this is the counterpart of, maybe it is better if I write Eulerian here and Lagrangian there. Okay, we will fix this notation. And this is the counterpart of the Lagrangian expression for equilibrium equations, which we have found calculating the first variation of the total energy. So now the problem is, how do we transform the capital div into the small div to find the relationship between P and T? Okay, this we will need some time, and I must prepare carefully this lecture in order to avoid that you are very confused by mathematical details. But this was the program fulfilled by Piola. I can tell you the story. He wrote this div P plus B Lagrangian volume equals 0 and Pn equal B surface Lagrangian on free boundary. And he published his first volume in 1824. Okay. French school, in particular Poisson, attacked him violently because they said that this is, Poisson said that this is physically meaningless. He said that balance of forces is Eulerian. Okay. So Piola proved balance of force and moment in Eulerian description as a consequence of the minimum energy principle. So the big trick, technical difficulty, was exactly to transform this div into this div. And I know for sure, because I've checked, that even in Berkeley, they call this the Piola transport. However, as you know, Piola transformed in this direction the divergence. So he transformed capital div into small div. In the modern literature, Piola transport is the other way, the transformation in the other way. But both of them are related to Piola, clearly, because if you can go back easily, you can go, if you can go ahead, you can easily go back. Okay, so what I want, I gave you some details, but we will give you more details. But what I want to tell you is that now, with Cauchy approach, we have small div of a tensor T plus B Eulerian volume equals 0, Tn equal B Eulerian sigma. Okay. We look at these equations and we understand that they are incomplete. Why? Because here you are using, for getting this, you are using only some necessary conditions for equilibrium. So you are using, in the language of Viola, the principle of minimum of energy only for virtual translation and virtual rotation. So one is not testing the deformation energy. And this is the big problem. When using the Cauchy approach, there is nowhere except for the crazy idea that you have the Cauchy postulate. By the way, they could prove that the T depends on N starting from the existence of surface contact forces only. So the true basic assumption, this is a result due by null. So at the end, the group of Cauchy could reduce everything to the fact that contact forces are only forces per unit area. So they can prove everything. One can prove everything simply assuming that contact forces are surface density of force, are a surface density, are given by a surface density of force. Okay, but this assumption remains. So don't believe people telling that the Cauchy postulate can be removed. The Cauchy postulate can be proven assuming that contact forces are surface density of forces. And that's it. So the fundamental assumption is that two sub-bodies can interact only via a force concentrated on the dividing surface, and this force is 0 if the area of the surface is 0. Okay? So Cauchy followers, there are too many even nowadays. Cauchy followers add out of the blue, the constitutive equation. T is equal to T hat of F. So they need to postulate. So let us make a comparison between approaches. Okay. In the Lagrange approach and the Cauchy approach. Okay, in both of them, we have the kinematics. The kinematics is the same. You have the placement from a reference configuration to an actual configuration. Then, in the Lagrange approach, you minimize energy. One part of the energy is deformation energy. Okay. So you give W of F as W bar of C of F. You make your, if you want, you stop there. Because with COMSOL, you minimize the energy and that's it. However, if you want to integrate by parts, you get div P plus B Lagrangian volume equals 0, Pn equal B surface Lagrangian on free boundary. Okay. And P is equal to dW over dF. Very simple. Where is all your constitutive assumption? Your constitutive assumption is there. So you have a clear division between basic postulate, remark only one, and constitutive assumptions. So you have a postulate of minimum of energy. This postulate tells you choose a deformation energy. You choose it. You choose it in an objective way so that W depends only on C. And that's it. You make calculations and you get your results. Look what Cauchy has to do. First postulate, balance of force. It is a vector postulate. I mean, it is an equality between vectors. Then you have balance of moment of force. And this is equally complicated as the first one. Okay. Then you must invent Cauchy cuts remark that the Cauchy cuts are not existing in Piola's approach. Piola's has only the boundary of his own body. Okay. And then the assumption is contact forces depend, are only forces per unit area. So for every Cauchy cut, you have a field of Cauchy vectors. This Cauchy vector field depends on the surface. Okay. You use 1 and 2 repeatedly for sub-bodies, and you prove Cauchy postulate, the linear dependence of stress, the linear dependence of Cauchy vector on the normal. These are all results, I agree. However, you need to assume that contact forces are only forces per unit area. And there is no physical reason for believing this. Simply because stress vector, Cauchy stress vector, is imaginary. Nobody is cutting a body and measuring the forces applied on it. And we have nice examples of situations where contact forces are concentrated on edges. For instance, at the tip of a crack. You know, there is, if you have a body with a crack which is being opened, we have some evidence that you have a force concentrated on the edge. But, okay, so these are the assumptions. Then you make calculations and you find div, small div, of T plus B volume Eulerian equals 0, Tn equal B Eulerian surface, and that's it. So you must add a fourth assumption. T is equal to a certain function of f. And you must painfully find problem. How do we include objectivity here? I want to underline this for you. Objectivity in Piola's approach is very easily introduced. Here is. If you, and it is all, you know, in the approach in Piola approach, it is very easy to check objectivity and understand objectivity. Let's go to this point a little bit in more detail. Okay. We have a body, we have a placement, we have actual configuration. Okay. If you rotate or translate the body in the actual configuration with a rigid body, there is no change in the deformation energy. You have a body, you deform it, then you translate or rotate rigidly. There is no extra deformation energy. Okay, so we can consider displacement key. So you have small x equal capital X, key of capital X. Then you introduce another x prime equal x, let's call it x prime of x. So we have, this is very elegantly written in Piola's book. So you have here another rigid body motion. So C is a placement, C prime is another placement, and you move from C to C prime with a rigid placement. So you have that x prime of of small x, because small x now is the reference configuration label, is equal to the placement of x0. So you choose capital X0 here, you choose a small x0 here, and then you have x prime of x0 plus q of x minus x0. Okay, and then you consider x prime of capital X composing the two. Okay, so you have, this is equal to x prime of key of x0 plus q of key x minus capital X minus x0. Okay, which is the f prime. So grad x prime. So if you want dx prime over d capital X. Okay, this is a constant. So you apply the chain rule for derivative. The gradient of a linear function is q, and then you have d key over d capital X. So you have qf. So if you displace your body after having deformed it with key, you have a placement and then you rigidly displace it. The new f is trivially q composed by f. So let us write C prime. C prime is f prime transposed f prime. So it is qf transposed qf. This is equal to f transposed qf. This is 1, and you get f transposed f, so you get C. End of the argument. Every energy, deformation energy, must depend on C. Okay, so it is very easy, and believe me, even if it's using component-wise notation, this is Piola's argument. Okay. Now, objectivity in the approach by Cauchy, first of all, tells you that T is equal to its symmetrized. So objectivity requires, because this is a result of from moment of forces. Okay. But then you must painfully understand how T depends on F. And this is not easy. We will see the formulas later. Okay, so Cauchy Eulerian approach based on balance and on the choice of suitable constitutive equations is more complicated. Too many independent assumptions, too many not justified you can make yoga, you can make yoga practice and you can start believing that you can see forces per unit area. Okay? But I don't believe that nobody can really seriously claim that he understands forces per unit area in a Cauchy cut more easily than deformation energy. I really cannot believe it. Okay. However, Eulerian approach is very efficient when studying fluids. So the idea of Cauchy is the following. I call a fluid a material such that this equality holds, where I is the identity, and P depends on ρ only, where ρ is the Eulerian mass density. So if you enter in the point of view of Cauchy, constitutive equations, you remember in our list, the assumption number 4 is to choose how T depends on F. Okay, now if you have the placement and you have a mass density rho star of capital X, and you have a sub body S of your body, the mass of S is equal to the integral over S of rho star capital X d volume. This is definition of mass density. Okay. Then you have displacement of key of S. So this is key of S. Okay. Now, the mass included in S, of course, this is another assumption. We assume that this equality is true. I mean, this means no growth of mass inside S. You may believe that this assumption is has to be accepted all the time. But I tell you that bones, including our own bones, are growing. Their mass is changing. Specific biological mechanisms. So this is another constitutive assumption. There are some deformable bodies for which this assumption is true. Okay, so we are allowed to change the variables and to write that integral of key over key S, the image of S under placement of the Eulerian mass density in the Eulerian volume. This equality is true. And then to find the relationship between this rho star and rho, we remember if you have F, which is gradient of key, the integral changes following the rule of the Jacobian. So the change of variable here, this integral here, can be written like integral over key S of what? Of rho star key minus 1 small x. So I change the variable and using the inverse of key, I go back to the reference configuration. And here I must represent dv in terms of the small v. So d small v is equal to j dv. J is the determinant of f. Okay. So d capital V is j minus 1 dv. Okay. So that we can deduce that rho is equal to rho star j minus 1. Okay? And this is the relationship between f, determinant of f, and rho star and determinant of f and rho. So clearly, if you assume that this pressure depends on rho, you are assuming that T of F is equal minus P, function of another one, determinant of F, identity. So it is a particular case of the Cauchy constitutive equation we have listed. I mean, we have listed that this constitutive assumption must be given in order to complete the formulation of a problem of deformation. Okay, so at the end, you have T equal minus P rho, identity. So we need to calculate, remark that this T is T applied to N is the vector T, okay? So T is a force. This T N is a force. This N is a normal. So naturally, we have contravariant components. And T is represented in this way. Remark that all indices are small because we have only Eulerian vectors. Okay? You know, Tin delta Kj gives you the density, the surface density of work in the virtual displacement delta K, and Ni we have lost. Okay, I will call tau I is equal to 0. Tau is a tangent vector to Cauchy cut. Okay, so naturally, Cauchy stress tensor is represented in this way as a tensor having one contravariant and one covariant component. Okay? Okay. So maybe it is worth, as this was a heavy lecture, it is worth that we introduce some easy concepts. Sorry, this is not, this is Tn, this is N. So I hope that you are aware of the fact that Tn projected along the tangent, one tangent direction tau is called shear component of Tn and that Tnn is the traction or compression component for Tn. Okay. So when you have an imaginary Cauchy cut and the Cauchy stress vector Tn has only normal components, so when Tn dot tau is 0 for every tau, no shear contact forces are applicable. Okay. Okay. So let's check what is capable to do a fluid. By the way, this is called Eulerian fluid because it was Euler of perfect fluid, because it was Euler who introduced this kind of fluids in continuum mechanics. So let us calculate Tn the identity applied to n gives you n. By assumption, P of rho is always positive. This is another definition characterizing Eulerian fluids. So what you get very easily? You get very easily that an Eulerian fluid cannot exert shear stress and tractions, because this quantity is positive. So the contact surface, if this is the normal, and the force can be only this with P positive. Okay. Now, why this is misleading? This is the standard treatment you find in the books. But why this treatment is misleading? Because Viola proved that W of F equal W hat of rho implies that Cauchy stress is equal to minus P rho identity. I mean, this proof I cannot give you here quickly because we need to transform this. We need to transform P, which is equal to dW over dF, which is equal to dW hat over d rho over dF. And this calculation is not so easy. Then we must to write div P and transform it into div T for identifying T in terms of P. Okay, so this is a program for a future lecture. We will need, I hope, we managed to do this in 2 hours, but we may need 4 hours. Okay. But this is fundamental. You know, I think that you must understand that use the minimum possible of using the minimum possible of assumptions and understanding what we are doing requires an effort, an intellectual effort. So I want to give you the example of the Eulerian fluid as treated by Cauchy as an example of oversimplification. They wanted to forget every difficulty. They wanted to remove every technical, difficult technical aspect of the reasoning, and they gave the brutal result. The brutal result is for fluids, T is equal to minus P rho identity. And P is positive. This choice can be understood because this statement you can clearly understand. However, it is rather difficult to understand for you that behind this expression you have an energy which depends only on the mass density. This is rather difficult to see, and we will need to understand this. And this is very important because you have a material which opposes only to changes of volume. A fluid, a perfect fluid stores the formation energy only changing its volume, or if you prefer, changing its Eulerian density. And I think that this is the essence of a perfect fluid. And this essence is blurred, hidden by this definition here. Okay? In fluid mechanics, they even manage never to talk about reference configuration. So there are some books in which the oversimplification arrives at the peaks of never talking about the reference configuration. So you say, okay, you are changing the mass density, but do you have a reference mass density? They tell you that a fluid cannot have 0 mass density. Okay, but let us go ahead, and we have some time, so we must deduce div T plus B equals 0 for a fluid. So div T is d T I J comma d small x j. Okay. Wait a second, I must be consistent. So this is contravariant. So up is covariant. So I need to place j here and I there. Plus bi equal 0. Okay. If I want to represent b as a covector, then I can write also dt j I dx j plus bi equal 0. Okay. So this is the equilibrium equation for our fluid. Then I replace and I call Tji equal minus P delta Ij. And I replace here. So I get d over dxj of minus P delta Ij plus bi equal 0. Now, when j is different from I, you get 0. So you are left with d over dx I minus P plus bi equal 0. So you get the famous equation, the gradient minus gradient of P plus B equal 0. So the gradient of the pressure, is given by volume force. Okay. And then you have on the boundary Pin minus Pin equal to the external surface applied force. So what you discover? That Bx sigma dot tau is 0 for every tau parallel to sigma. So no shear forces are applicable by a perfect fluid. So why of course, let's go ahead. So when you give P of rho, you have a channel. Here you have a rigid wall. So you don't have a displacement given there. You have a rigid wall everywhere. Look how strange is the behavior of a fluid. So you take a fluid inside a channel with blocked walls. Every wall is blocked. The equation is minus grad P plus B equals 0. And you have that the P is equal P external. If you have blocked the wall, these are also, they are all constrained pressure. Okay. So you can apply on the wall, on the container of a box where you have a fluid, you are sure that the box is only exerting a pressure. So no shear force on your fluid. But what is rather astonishing is this one. You assign in one point the pressure, only in one point. And then integrating integral of grad P between P0 to P, you get the pressure in the point P minus the pressure of the point P0. So as this is also equal to the integral of B, of course, this is the line. So you have a path from P0 to P, and you have that the pressure in the point P is given when you know the volume force B and the pressure in one point. Okay, so for a perfect fluid, the boundary value problem is very easy to solve. It is enough that you assign the pressure in one point and the pressure is given everywhere. Not only if B is equal to 0, then the pressure is constant everywhere. So you cannot apply at the boundary of a perfect fluid a field of pressure. So here one pressure, there another pressure, there another pressure, if you have B equals 0. So you have relevant compatibility conditions for a perfect, for the boundary conditions for a perfect fluid. So the model perfect fluid cannot describe many physical situations. Okay, we are talking about equilibrium. Okay. Now people, we have some time. So now people from believing in Cauchy postulation says, okay, in a perfect fluid, you have accelerations. If you don't have the boundary conditions, you must assign for having equilibrium. So what you can write? You can write that the integral on the boundary of an Eulerian volume, C, of minus Pn plus integral on the volume of B, volume, minus mass times acceleration, density of mass times acceleration. This is equal to 0. And as usual, you consider the standard localization argument. So what you do? You consider a generic sub-body okay? And repeating the integration by parts and the localization argument as we did before, you find minus grad P plus B volume minus rho acceleration equals 0. And Pn equal Px on the free boundary. This problem, however, is lacking some kinematics. The standard, okay, let us start to consider, I'm telling you this in the order of used by somebody who already knows the result, okay, which is the approach used by Cauchy. So I want, the lack of logic connection between one argument and the other is not mine. This is what I want to say. Okay, so let us start adding another assumption. The fluid is incompressible. So rho is equal to rho star. Okay. This means that P, which is a function of rho, becomes this is for compressible fluids, becomes undetermined. You must understand this. I try to explain you in a reasonable way. Imagine that you have that P is a increasing function of rho. So we can say, for instance, that in the neighborhood of a certain value, rho 0, P is equal to P0 plus compressibility factor alpha times rho minus rho 0. This is a possible linearized constitutive equation for P. Okay. And alpha is positive. So when you increase rho, you get a greater P, and when you decrease rho, you get a smaller P. This is all reasonable. Okay. Now, what happens if alpha tends to infinity? When alpha tends to infinity, you have a very high incompressibility, and this expression the pressure cannot go to infinity. Otherwise, you could get infinite forces, so infinite energies, simply stiffening your fluid. Erden, I know your face is showing me that you cannot follow the logics of all this. I am repeating, in a sense, I'm trying to motivate why I don't like this approach. Okay, but if you go and read these things in the books, you will find more or less exactly these words, which in my opinion are an a posteriori interpretation of a rigorous result obtained by Piola. Okay? So, what you want, that alpha going to infinity must be multiplied by this, which goes to 0. So that when alpha goes to infinity, rho tends to rho 0. So the fluid is incompressible. So actually, to say that the fluid is incompressible, simply stating that the density, mass density, is always the same, is too much. No, not enough. Okay. So you must say rather that the compressibility tends to infinity. The coefficient, the stiffness goes to infinity, so that rho minus rho 0 tends to 0. And you know very well that this limit is not determined. So what happens? It happens that for incompressible fluids, rho is equal to rho star and P is unknown. So when rho is given to rho star, in every point, Eulerian point, you know the mass of the material particle there. So you can easily write the balance of mass in every part of this channel. So what you can do, you introduce an extra kinematical descriptor V. Okay, V of x and t is always d key over dt calculated in key minus 1 x t, as we did define before. Because you remember, I have displacement, capital X, small x. You have a material particle x. Key of x and t is the placement of capital X at instant t. And this is the position x. We wrote this formula many times. D over dt having xp fixed of key of xp and t is the velocity of the particular material particle x of p at instant t. So this is the velocity here of the material particle xp. When you calculate this in k minus 1 of small x, you place the velocity in x, small x, and you say this is the velocity of the material particle, which at instant t finds in small x. So this is the Eulerian velocity field. It is a map which tells you the velocity of every particle which is passing there. So you are not writing, when you write this equation, you write a material particle. Okay? If instead you consider v of small x and t, you stay in x and wait for the particles which are passing by. Okay, so when you write v of capital X t, you follow the particle. When you write v of small x and t, composing with key or with key minus 1, you block your position in a point, Eulerian point, and you see the flow of particles in that point. Okay. Now, the big problem is the acceleration of a material particle, x and t, is equal to the second time derivative of displacement as a function of x and t with blocked x, capital X. Now, we will need to discover how to relate small v of x and t with small acceleration of x, of small x and t. So, relationship between acceleration and velocity, Eulerian fields. In this way, we will be able to write in this equation the velocity, and we will need to add an equation for velocity. So that we probably will be able to find the equations for the incompressible fluid. Okay. So, okay, at this moment that I stop, I leave you with a message. You could believe that fluid mechanics is not variational. False. The question is that we are using necessary conditions which are valid for every continuum, and we play with these necessary conditions for finding well-posed problems. Okay? We will see that in recent times, fluid mechanics is becoming again very Lagrangian and very variational. Okay, so we stop here.